Today we are going to do its three-dimensional case. So for that, we will start by recalling the expressions of wave function in the one-dimensional case. So psi was given as root 2 by L sine kx, where k was equals to n pi by L. Also, we calculated the expression of energy as E equals to m square, h cut square, pi square over 2m L square, which is also equals to h cut square, k square over 2m. So now we will extend this case to the three dimension. That means when an electron is moving in the lattice of three dimension. So we will consider it to be a particle in a three-dimensional box, and here the Schrödinger wave equation will be Laplacian del square psi E minus V equals to 0. So this is my time-independent Schrödinger wave equation in three dimension. And we know that the V here is 0 because the particle in a box of 0 potential is a free particle. So V here is 0. So when we will extend the solution of one dimension in three dimension, the expression will contain not only one k, there will be the expression of kx, ky, and kz, because now the wave can travel in both in the three directions. So we will consider it to be psi. There will be a constant a, sine of kx x, sine of ky y, sine of kz z, where kx, ky, and kz will be given by the expression just like here. Now kx will be nx pi over L, ky will be ny pi over L, and kz will be nz pi over L. And of course, the expression for energy will remain same as n square, h cut square, pi square over 2m L square. Proceeding further, the expression of A will be like, in one dimension, A was root 2 by L, but here it will be root of 8 by L cube, because the three terms will contribute like root 2 by L multiplied by root 2 by L multiplied by root 2 by L. So when we find the expression of A by the normalization condition, we will find A to be equal to root of 8 by L cube. So our final wave function, now I am writing this wave function as psi k, that is we are talking about the mode where the wave vector is having k value, and it is now dependent on r as we are doing three-dimensional case, and the final expression for wave function would be 8 by L cube sine nx pi x by L sine ny pi y by L and sine nz pi z by L. So this is the complete form of our wave function. Next, also we can write that k square here is equals to kx square plus ky square plus kz square. And as we have written the value of kx, ky and kz here, so from this expression, we will get the value of k square as pi square by L square. And in the bracket, you will get nx square plus ny square plus mz square. Also, I can write another form of wave function, means I can write this wave function in a more general form involving the exponential term. So psi k r can also be written as a exponential of iota k vector dot r vector, where we know that k vector will be, of course, its component along x-axis I cap, ky, j cap, kz, k cap. And what is r? R is my position vector, which is given by x I cap plus y j cap plus z k cap. So psi k r can be written as a exponential of iota with the dot product of k and r, will get kxx plus kyy plus kzz. We have derived the expression of kth value of wave function, which is given by this expression. Also, we know that wave function must satisfy symmetry condition of translation. That means when it goes from one atom to the another atom, it should be same at the starting point of other atom. So it should be a periodic kind of function along x, y, and z direction. So I can clearly write it as psi k of r should be equal to psi k of r plus some constant. That constant will depend upon whether we are moving towards x-axis, y-axis, or z-axis. So in elaborated form, I can write this as x, y, and z should be equal to psi k of x plus a, or here I have taken it to be L, y plus z. So in quantum mechanics, what we are doing is, this was my box along x-axis. So the wave function at x equals to 0 should be equal to the wave function at x equals to L. So I'm writing it as wave function at x is equals to wave function of x plus L. Similarly, for y and z axis also, we will have to follow this boundary condition or symmetry condition. So putting this in the above equation, so our psi k is simply given by a exponential iota kxx plus kyy plus kzz. Now At the place of x, I will put x plus L. So A exponential of iota k x plus L plus kyy plus kz z. So doing a little bit of mathematics, what we will get is I forgot to write x here. There is also x and kxl plus we will be having exponential of plus actually it will be exponential of iota kyy iota kzz, and on the right hand side we will be having exponential iota kxx iota kyy and iota kzz. So this term will cancel with this term, and at the end what we will get is exponential of iota kxl is equal to 1. Now this is possible only when exponential is having the factor of 2n pi. I mean to say exponential of iota 2n pi, where n could be 0, 1, 2, 3, will be equal to 1. So here what we have concluded is that iota kxl is equals to iota 2n pi. So from here kx comes out to be 2n pi over L. Similarly, we'll get the expression for ky and kz. So writing different values of kx. So kx will be for n equals to 0, it will be 0. Then for n equals to 1, it will be 2 pi by L. For n equals to 2, it will be 4 pi by L, and so on. Also, I would like to mention here that here both positive as well as negative values should come. So we will be having plus minus plus minus. So these are the values of wave vector, allowed wave vector along x-axis. Similarly, the allowed wave vector along y-axis will also be having same values, and same is for the z-axis. So now we will be calculating for the density of quantum state. Density of states at 0 Kelvin we are talking. We already have calculated kx to be equals to kx square plus ky square plus kz square. And all the k values are separated by the distance of 2 pi by L, because we have written kx were having allowed values of 0, 2 pi by L, 4 pi by L. That means, and so on. That means the allowed k values will be only at 2 pi by L, and then after a gap of 2 pi by L, there will be another value of allowed value of kx. Similarly, it was along ky and kz. So if we take this point k allowed point K, the allowed value of K, and its volume will be Kx into Ky into Kz. In fact, delta Kx into delta Ky into delta Z. And that will come out to be 2 pi by L cube. And taking K square as radius, if I draw a sphere in K space, here is Kx, here is Ky, and here is Kz. So a sphere of radius K square, in fact Kf square, because here we are talking about 0 Kelvin, so we will take only the highest level to be Fermi level, and the wave vector associated with that level will be Kf. So the points, all the points in this sphere of radius Kf can be found by finding the volume of this sphere, which is equals to 4 by 3 pi r cube. 4 by 3 pi kf cube is the volume of this sphere. But all the points are not allowed, because we have already found that the allowed values of k are separated by the distance 2 pi by l. And if I want to find the total number of allowed values, that will be dividing the whole volume of sphere by the volume of 1k point, which is 2 pi by l cube. And this should come out to be equal to n by 2, where n is what? N is the number of electrons. Say, if we are having 8 electrons, we know one electron will be having spin half, one will be having spin down. So total number of k states or quantum states, that will be half of this. For example, we are having 8 electrons. So these 8 electrons will occupy the lowest 4 levels. So the number of quantum states are these. Hence, we will get this expression, and from here we can easily calculate the expression of kf in terms of n or n in terms of kf. Okay, so we have derived the expression of kf in terms of n, and also energy, Fermi energy, is related to the kf by this expression, and hence the formula of Fermi energy in terms of n is calculated, and from here we have calculated the expression of n in terms of Fermi energy. Now talking about the density of states, here I'm talking about the density of electronic states. If I denote them by ZEDE, and if I integrate it from 0 to EF, now let's understand a little bit of the physics behind it. So these are my energy level, and these are the electrons on it. So if we're having 8 electrons, as I already discussed, the total number of filled electrons will be, filled level will be 4. And the highest filled level, we call it Fermi level. So if we want to calculate or count the number of levels from 0 to EF, we will integrate this factor from 0 to EF, and it should come out to be equal to n, because now we are talking about the electronic states, not about the energy states. That means how many electrons will be here. So simply putting the value of n from this expression, we will find that ZE from 0 to EF comes out to be and then differentiating this equation, we will get ZD to be that means ZD is now showing the dependence on E as directly proportional to the root of E. Then what will be the density of states at energy EF? we will get this as EF, and the formula of EF we have already calculated. So we have calculated ZE to be equal to V over pi square 2m by h cut square 3 by 2 e power 1 by 2. Also, ZEDE is telling me the number of density of states. So, for the states which are below the Fermi level, we will be having electrons, and above there will be no electrons. So, the density of the states will be decided only by the levels which are below the Fermi level. So, here I am defining another function which we call as Fermi function, and it is given by f function of E as 1 over exponential E minus EF over KT. Here K is actually Boltzmann constant plus 1. This I have taken from Fermi-Dirac statistics. And this function will be having the value 1 for E less than EF and value 0 for E greater than EF. That means if I multiply this function with this ZDDE, I will get the information about all the energy states, and the total number of electron n will be actually now from 0 to infinity, integration of from 0 to infinity ZEDE FE. Why 0 to infinity? Because so here this F can be calculated already taken into from 0 to infinity the unfilled level, and putting the value of Z that we have 0 for the levels to be which are above the Fermi level. So this integration reduced to 0 to EF only. We will see it further. 3 by 2, E 1 by 2. Also we are having the term of Fermi function and DE. By simply integrating it, we can split this integrand into two parts, one from 0 to EF and another from EF to infinity. So, taking the constant terms outside the integration, we will get E1 by 2 FE dE from 0 to EF, and the second term will be E1 by 2 FE from EF to infinity. And we know FE is 1 for E less than EF, and FE is 0 for E greater than EF. So for this term, FE will be 1, and for this term, FE will be 0. So this term will cancel by itself, and hence N will come out to be V over 2 pi 2m over h cut square integration of E 1 by 2 dE from 0 to EF, which on calculation and putting the limits will come out to be V over 3 pi square 2m EF over h cut square 3 by 2. This value of n we have already calculated. And from here, EF can be written as h cut square over 2m 3 pi square n over v 2 by 3. So this is the energy of Fermi level, and this is the number of electrons in terms of Fermi energy. These expressions we can calculate directly from that K sphere also and from the Fermi function also. Next, we will be calculating average energy of electrons at 0 Kelvin. Now, to calculate average energy, which we denote as this, we need to integrate energy with the number density, that is ZEDE. And of course, the Fermi function should come into the role because this will integrate it from 0 to infinity. Also, we will have to divide by the total number of electrons. So this is the expression for average energy of electron. Just doing a small calculation, we here know that F is again 1 and 0 for E less than EF and for E greater than EF. So for the integration from 0 to EF, we will have Fe to be 1. And for the integration from EF to infinity, we'll have Fe to be 0. So we will skip one step and simply write it from 0 to EF, E, ZD, PE over N. And putting the value of Z in terms of E and taking the constant outside, we will get V over 2 pi square N, 2m over h cut square power 3 by 2, and Z is having the dependence on E as power root, and here is E, so the total dependence on E will be 3 by 2 from 0 to EF dE, and just simply solving this expression, we will get E naught to be equal to V over 2 pi square N 2m h cut square 3 by 2 EF 5 by 2, and there will be a factor of 2 by 5, which is to be multiplied with this. So we know what is N. The expression of N is V over 3 pi square 2 over h cut square power 3 by 2 EF power 3 by 2. So V pi square 2m over h cut square and 3 by 2 from the 5 by 2. So I'm left with 1 EF here. So these terms are also, I need 1, 3. So what I'll do, I'll multiply with 3 and I'll divide by 3. So what I'm left with 3 and 2 extra term, and other terms will be my N. So I can write it as 3 by 2. All other terms give me N. And then I'm left with this E, F, and one term is 2 by 5. So cancelling the 2, I will get 3 by 5 EF. So this is a very important result, that average energy of the electron is actually 3 by 5 times the Fermi energy of the system.